Hello everyone. Thank you for joining Document Intelligence Workshop. This is Saurav Nanda. On behalf of my co-authors Partha, Parivesh and Pawan, I'll be presenting our paper SpecToSVA, that is a commercial tool which takes circuit specification document and translates the English sentences to SystemVerilog Assertions. Design verification is a very time-consuming process due to the manual effort required in reading large IC design specification and write checkable formal properties. This process can take up to 50 to 70% of total development cycle. This problem gave us the motivation to develop a tool that can automate this manual effort. Here is the big problem that we are trying to solve. The design verification process starts with a requirement document that has all the high-level requirements of our IC design. Then the IP engineers write specification document that has all the protocol level information. Now the verification engineers take this specification document and try to extract the verification items. The verification item can be defined as those English sentences that can be potentially translated to a formally checkable property. Now they use all these verification items and manually synthesize formally checkable properties. And this process can become really cumbersome because the whole loop has to be repeated again and again for different versions of the same document. SpecToSVA solves this problem using an NLP-based technique by automatically translating English sentences to SystemVerilog assertions. SpecToSVA architecture comprises of 5 major components: the sentence detection, sentence analysis, DNN model training, translate, and verification. Sentence detection takes the English specification document, parse through it, and classify all the sentences into two parts, one that can be translated to SVA and the other which cannot be translated to SVA. In the sentence analysis part, we use a custom spacing model to detect all the NERs in the English sentences. The NERs can be categorized into two buckets, variables and constants. And then we save the mapping of the NER correspondence in both English and SVA languages. Third bucket is the DNN Model Training, where we take the English sentences, create the constituency tree, perform NER token replacement, and train a probabilistic shift-reduce parser, that's the spin model. In the translate part, we use the same shift-reduce model to take the English sentence and perform the translation to SVA. Once the SVA is created, we verify it in the compiler and we also check it manually. If something needs to be corrected in the SVA, we correct it and provide it as part of training data for next model training. Now let's discuss each component of SpecToSVA architecture in detail. The first one is sentence classification. We use Snorkel technique that uses disagreeing heuristics to estimate the marginal probabilities. Now in this particular example, if you see the sentence Y1 has 3 heuristics, L11, L12, L13, which can be like whether it have any identifiers. It may be similar to a template, or it can contain some keywords like must, may. Now depending upon the answer to these heuristics, you calculate the probability. So in this case, the probability for being an assertion is 0.75. Once the sentence classification is done, we have all the sentences that can be potentially translated to SVA. Then we perform NER detection on those sentences using a custom spacing model that helps us to classify those NERs into two buckets, variables and constants. We also train a Benepar model to create constituency tree from English sentences. But the problem is Benepar model will give you multiple constituency trees. Hence we use a self-attentive parser to create a best possible constituency tree from an English sentence. Then we further enhance that constituency tree by doing two things. First, we do token replacement, the NER token replacements with out of vocabulary. And the second, we replace the sub-sentence markers, which are S, S, S here, if you see, with S1, S2, S3, and S4 to avoid any conflicts in the sub-sentence of a sentence within a sentence. Now let's discuss about the deep neural network that we have trained to do the machine translation. It comprises of a generator network and a pointer network. The generator network takes buffers and transitions for encoder and corresponding target language for the decoder part. It learns the structure of the target language from the source language. And the output of this network comprises of two major things. One is the out of vocabulary NER tokens and the SystemVerilog assertion, the operators, functions, or constants from the decoder language. The buffers in case of generator network are the token positions of the English language words. Now pointer network works very similar to the generator network. However, it learns the relative positions of the OOV NER tokens from the training data set that are replaced by the decoder language tokens. And the training data comprises of both English and corresponding SVA language tokens. Now buffers in case of pointer network are the token embeddings of English language words. And transitions for both generator and pointer is a post-ordered token sequence of updated constituency tree. And it is assumed that every part of speech tag of the constituency tree will be a transition. Now let's talk about the translation process. We take an English sentence and we create the constituency tree from that. Once the constituency tree is created, then we detect the NERs in that sentence. So in this particular case, if you see, this is the NER constant, and these are the two variables that we have detected. Now we replace these NER tokens in the constituency tree. We do our enhancement of the constituency tree. And then we predict the structure of the SVA using our generator network. Then we use our pointer network to predict the NER positions. Once we have the structure and once we have predicted the positions for the NERs, then we can create our final SystemVerilog assertion for this English sentence. Here are some of the example translations that we have got from our experimental results. If you see the first couple of them, they are quite straightforward. But the third one, if you see, like we have replaced some of the user-defined functions for certain phrases in the English sentence. And these definitions should come from the users because these are user-defined functions and we have just made a placeholder for them like this one, user definition time 01. This is a timing function which the user has to define, which we cannot derive from the original English sentence. Now let's take a look to the experimental results. The results looks quite promising. If you see, we have done training and validation on various data sets, and we are able to achieve reasonably well precision that can be accepted by the verification engineers. To conclude the presentation, I must say that SpecToSVA provides a complete flow for IC design engineers and verification engineers to identify potential verification items and automatically translate those verification items to formal language models. And the experimental results that we have got does certify that we are able to perform really good on some of the commercial IP specification documents. As part of future work, we would definitely like to establish co-references between two sentences which may belong in different sections of the document and combine those sentences and then perform the translation. That's what we are looking to do in future. With that, I would like to thank you all for listening to this presentation. If you have any questions, please feel free to ask and post your questions. Thank you very much.